Hello everyone. Today we are going to analyze this frame using flexibility matrix method. In this frame there are two columns, column AP and column CD. Also there is a beam BC. In the columns there is no load. In the beam BC we have a uniformly distributed load 30 kN per meter. It is acting for the full span. In the joint B, there is a nodal point load 45 kN. It is acting towards the right side. The height of the columns are 4 meter and the length of the beam is 5 meter. For the columns, the moment of inertia is I, and for the beam it is 2I. In the points A and D, there are hinged supports. In this frame, the number of unknown reactions and moments are 4. In the point A, we have the horizontal reaction HA and the vertical reaction VA. And in the point D, we have the horizontal reaction HD and the vertical reaction VD. So the total number is 4. The available equilibrium equations are 3. The degree of static indeterminacy will be 4 minus 3, so it will be 1. Let us release HD. You can see that I have released HD. To find VA, let us take a moment about D. In this case, we have to follow right hand side rule. VA is acting in the clockwise direction, so that it will be positive, and the distance is 5. So 5 VA. This load is acting in the anticlockwise direction, so that it will be negative, and the distance is 5. We know that with the UDL we have to multiply the distance and then the distance by 2. The nodal point load is acting in the clockwise direction, so that it will be positive, and the distance is 4. For VA we will get 39 kN. Then using this rule we can find VD. Using this rule, we can find HA. For HA, we will get 45 kN. We know the equation which is used in the flexibility matrix method. Here P will be HD because that is the one we have released. In the point D, there is no horizontal yielding of the support. In this case, delta will be 0. We know that 0 matrix is 0. Finally, we will get this equation. To find these two, we are going to use the unit load method. We have to make sections. In this frame, there are three different parts: A, B, B, C, and C, D. So we have to make three sections: one in AB, one in BC, and one in CD. You can see that I have made three sections. This section I have made at a distance of x from A. This section I have made at a distance of x from D, and this section at a distance of x from C. Now let us make a table. In the table, first let us enter the members. There are three members: AB, DC, and CB. For the section in AB, the origin is A. For the section in DC, the origin is D. And for the section in CB, the origin is C. Now let us enter the flexural rigidity EI. For AB and DC, the moment of inertia is I, so the flexural rigidity will be EI. For CB, the moment of inertia is 2I, so the flexural rigidity will be 2EI. Now let us enter the limits. For AB, it is 0 to 4. For DC, it is 0 to 4. And for CB, it is 0 to 5. To find the moment in AB, we can use right hand side rule. Up to this section, we have HA and VA. For VA, there is no perpendicular distance, so we should not consider VA. HA is acting in the clockwise direction, so that it will be positive, and the distance is x, so 45x. To find the moments in these two sections, we can use the left-hand side rule. Let us find the moment in DC. Up to the section, we have only the vertical reaction VD. For this, there is no perpendicular distance, so we should not consider this. In this case, the moment will be 0. Let us find M in CP. Up to the section, we have BD and the uniformly distributed load 30 kN per meter. BD is acting in the anticlockwise direction so that it will be positive and the distance is x, so 111x. The UDL is acting in the clockwise direction so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. X into x, it will be x square. 30 upon 2, it will be 15. Now we are going to find the moment small m. We need to remove all of the loads from the frame and we have to apply unit load at D in the direction of HD. By taking moment about D, we can find VA, which is 0. By applying this rule, we can find VD, which is also 0. By applying this rule, we can find HA. Now let us find the moment M in AP. Up to the section, we have only HA. It is acting in the anticlockwise direction so that it will be negative and the distance is x. Minus 1 into x, it will be minus x. Now let us find the moment in DC. Up to the section, we have only HD. It is acting in the clockwise direction so that it will be negative and the distance is x. Minus 1 into x, it will be minus x. Let us find the moment in CP. Up to the section, we have only HD. It is acting in the clockwise direction so that it will be negative and the distance is 4. Minus 1 into 4, it will be minus 4. Using this formula, we can find delta L. For CB, the flexural rigidity is 2EI. So instead of EI, we apply 2EI. For DC, M is 0. So no need to do the integration. We can directly apply 0. Then using a calculator, we can do these two integrations. For delta L, we will get this. Using this formula, we can find delta. For delta, we will get this. We have found delta L and delta. In this equation, let us apply both of them. Negative into negative, it will be positive. For this matrix, we have to find the inverse. We have to just write this member upside down. Finally, for HD, we will get 30.06 kilonewton. We know that the columns AP and CD having the same height 4 meter. So the vertical reactions which we calculated previously will remain same. For HD, we have got a positive value. That means our assumption is correct. We assumed that HD is acting towards the left side. Since we have got the positive value, it is really acting towards the left side. Now, using this rule, we can find HA. To draw the shear force diagram, only with the reactions and loads, we can draw free body diagram and find the shear force values. These are the shear force values for the column AB. These are the shear force values for the beam BC. And these are the shear force values for the column CD. Here you can see the shear force diagram. In the beam BC, in this point the shear force becomes 0. In this point there will be maximum positive bending moment for BC. We can make a section in this point and find the distance. Here I have drawn the free body diagram with the movements. We know that in this section the shear force becomes 0. We can find the shear force in that section. In this way, we will get x, which is 1.3 meter. To find the moments at A and B, we can use the right-hand side rule. It is the hinged end, so the moment will be 0. Let us find the bending moment at B. HA is acting in the clockwise direction so that it will be positive and the distance is 4. For bending moment at B, we will get a positive value. That means the moment at B is a sagging moment. Now let us find the maximum positive moment in BC. We know that it occurs in this section. MB is acting in the clockwise direction so that it will be positive. The vertical reaction at B is acting in the clockwise direction, so it is also positive and the distance is 1.3. The UDL is acting in the anti-clockwise direction, so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. Finally, we will get 85.11. To find the moment at C, we can use the left-hand side rule. HD is acting in the clockwise direction so that it will be negative and the distance is 4. For the moment at C, we will get a negative value. That means the moment is a hogging moment. We know that in the hinged end, the moment will be 0. Here you can see the bending moment diagram. If we make the diagram upside down, that means in the opposite directions, that is called the bending moment diagram on the tension side. Alternatively, easily, we can draw the bending moment diagram by superposition method. For that, first we need to draw the free movement diagram. In the beam BC, we have uniformly distributed load 30 kN per meter. Using this formula, we can find the moment and we can draw this diagram which is in the shape of parabola. We should not consider the nodal point load 45 kN. We know that the moment at B is a sagging moment and the moment at C is a hogging moment. Using the direction of arrows, we can draw the end moment diagram. The sagging moment will be positive and the hogging moment will be negative. Then we can combine both of the diagrams so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.